Good afternoon. Welcome to the CERIAS Security Seminar at Purdue University. I'm very glad to introduce today's speaker, Michael Kirkpatrick. Michael is a Ph.D. candidate in our department. I believe he joined in 2007, and before that he received his master's degree in computer science and engineering from Michigan State, and before that he worked at IBM, and before that he got his bachelor's degree from Indiana University. Michael worked with Professor Elisa Bertino, and his research interests are in designing secure systems with a special focus on the interactions between hardware, architecture, and operating system. And today he'll talk about physical unclonable functions, which is a very interesting topic.
Thank you. So the work that I'm presenting today, there are actually three main works that I'm going to be presenting. And all of this is joint work with myself, my advisor, Professor Bertino, and also Sam Kerr, who's an undergrad student here, who's also doing the 5-year master's program. So he's had a lot of help in this as well. So first, I'll start with a little background on what physically unclonable functions are, or PUFs, as they're colloquially called. And then I'll talk about the 3 different projects that we've done with these, and like Ningui said, I work on how to build secure systems. So these are 3 projects that have looked at using these techniques and building security products out of them. And then we'll have some conclusions and questions at the end. So first, let's start with what are PUFs? Well, a PUF really is just a way of quantifying the variations that naturally occur in hardware. If you take a circuit, for example, if you take a piece of hardware and you design it to be identical, when you manufacture 2 copies of it, there will be inherent variations that you cannot control. Most of these variations are at such small scales that they don't really matter. It doesn't matter if the wire on 2 different circuits, on 2 different copies of the same device, if one of them is a couple of nanometers thicker than the other. For the most part, these variations don't matter. But PUFs are a way of turning that around and saying, well, instead of this being a negative thing that we can't manufacture things to be identical, let's see what we can do with that and take those variations and create a unique function out of it. Create a way of identifying different pieces of hardware based on that. And because these variations are so small, you can't measure them, you can't control them, so you can't forge them. They also can incur a little bit of noisy data. There can be a little bit of inconsistent behavior. So you do have to make sure you incorporate some error correction to make sure that you get stable behavior out of the PUF. But from a very high level, this is what it looks like. You have 2 devices that are designed to be identical. And you provide a certain input to both devices. And if the input is identical, you're going to get different responses. And again, the only way that you can actually determine what that is going to be is by actually executing the PUF. So how do you design a PUF? Well, we've worked with one particular example called ring oscillator PUFs. And the idea of a ring oscillator PUF is that you have a set of ring oscillators, which is just a fancy way of saying you have an odd number of NOT gates in a loop. So you have the output of this oscillator it'll just switch back and forth between a 0 and 1. Well, when you manufacture a sequence of these ring oscillators, because of these tiny variations, each oscillator will execute at a different speed. They will have a different frequency to them. To quantify that, you can take these oscillators and connect them to a pair of multiplexers. So the multiplexers here, all they'll do is they'll just randomly pick a pair of the ring oscillators and then redirect the output into a couple of counters. After a certain amount of time, you compare the counters and say if the counter on top has a higher value than the counter on bottom, then you output a 1. Otherwise, you output a 0. And to construct larger PUFs out of this, you would use more multiplexers and more counters. And so you could have a very large bit string that gets created by this. if you model the PUF just as a mathematical function, if you sort of forget the hardware aspect of it, really what it is, it's just a mapping between challenges and responses. So specifically, you can have n-bit challenges and m-bit responses. So the challenges and responses don't have to be the same length. And a PUF is just a function. It's just a set of ordered pairs. But the mapping between those challenges and responses is determined exclusively by the variations in the hardware itself. And even though the challenges and responses don't have to be the same size, for simplicity we'll assume that they are. Because most of the work that we've done with them, these are the types of PUFs that we've been working with, is that the challenges and responses are the same size.
So for any piece of hardware, this function is deterministic? So if you use
Yes.
the same challenge, okay.
For the most part. There is a little bit of noisy data involved, so you do have to do some error correction, but we've found in our experiments that by repeatedly executing the PUF on the same device, you do get consistently the same response. Okay, so let's abstract this a little bit and talk about the ideal PUF assumption. So it's a function from challenges to responses, and ideally we would like the Hamming distance between the challenges and responses to be distributed normally from 1 to n. What this means is that we don't want there to be any sort of predictable linking between a single challenge and its corresponding response. On the other hand, if you take two challenges that have only 1 bit of difference between them, and you look at the Hamming distance of the responses, you want that to be approximately n over 2. So if you have two challenges that are very similar, you want their responses to be very different. And this is an ideal assumption, and it's actually very hard to achieve. One way to sort of forge this property, if you're trying to build a real system with PUFs, is if you just apply a cryptographic hash to the output of the PUF. Then it helps to get closer to this ideal. In the long term, it would be nice to have PUFs that you don't have to rely on a cryptographic hash to induce these properties, but for now, that's what we've been working with. The other assumption is that observation of the PUF, so to determine the actual behavior, requires actually executing the PUF. And this is a fairly reasonable assumption for ring oscillator-based PUFs, that the variations that occur in the frequencies of the oscillators are so small that you have to actually execute the PUF to determine which oscillators are going to be faster. So, in, I guess, more plain words, the ideal PUF assumption says that this function is unique to a particular device, it's unique to a hardware instance, and the challenges and responses are unlinkable. You can't guess what the response will be for a particular challenge. And then also the challenge-response pairs are completely independent. Knowing one challenge-response pair doesn't help you guess what the response will be for another challenge. There are threats to these assumptions. There was a paper in CCS that came out a couple weeks ago that really goes after this last assumption. And what they found was that if you know a certain number of challenge-response pairs, you can actually model the entire behavior of the PUF with high probability. So it really undercuts that last assumption that I stated. But it's actually okay in the works that we're doing, because in all of the works that we've done, we never make any of the challenge-response pairs public. We only make public commitments to the challenge-response pairs. And I'll talk about that more when we get to the protocols that we've defined. So even though this threat is real, it doesn't quite affect our work. But it does raise some supply chain issues, because now you have to trust the manufacturers of your devices that once they manufacture the device, they don't pull the PUF a few times and record those responses and then build models from it. So there are supply chain issues to deal with here. The other type of major hardware attacks that are very common are probing attacks, where you insert probes into the hardware and basically eavesdrop on the communication that's occurring, and eavesdrop on the behavior of the circuit. And while it hasn't been thoroughly evaluated, the general belief among researchers who have worked with PUFs is that probing is more likely to destroy the circuit than it is to before you would actually get enough observable data to model the PUF. So although we don't have quantification and we don't have proof of this claim, this is still the general belief. And part of that is because of the fact that the circuits, especially in the ring oscillator PUFs, everything is occurring within a single chip, and you have to actually execute the device. And there's the measurement tools that are out there are not quite powerful enough to get enough observable data just from trying to model it, just from trying to measure the variations. So the general belief is that probing is unlikely to.
I was just going to say there's been some work where they actually fab these with, in effect, traces surrounding the device that are inherent in the timing of the PUF. And so to actually get to the probing the part that you need to probe, you actually have to destroy its characteristics.
Yeah.
So what's the difference between probing and just evaluating it? So from the first attack, you evaluate it a few times, you get enough information to model it. So then what does the...
So the difference between these two threats is that in the first threat, you poll the PUF in the typical way of saying, here's my challenge, and you get the response. You just get a few of these pairs, and then from that you can build an abstract model of it. With probing, it's much more invasive. You're inserting probes into the circuit itself to try to measure the variations.
But why would you ever want to do that if you can simply query it?
Because, well, if you can simply query it, then you don't have that same attack.
But if you can carry out probing, I guess you can also query it, right? You have physical access.
Yes, any of these you have physical access to.
So I guess actually the first attack makes the second probing a non-issue in some sense.
Yeah,
Well,
sort of.
I mean, your solution where you're actually not revealing, it depends on the point at which you're performing that commitment that gets revealed. It
Right.
may be
Right.
that unless you're doing probing, you can't get the response.
And that will really come into play with the third work that we're going to talk about.
Okay. Yeah.
He
He may answer this.
Yeah, I
Yes.
just want to say, if the first one doesn't compromise his program, there's no way the second one would. I'm just saying, because there's the first work, then probing is not an issue now, because you can actually model this by building.
Well,
He
in
can
the
show us that's not
yes,
true.
in the third work, there is no way to directly request a response from the PUF. Okay, so let's look at the first work. So the idea here for physically constrained access control, we sort of started with the assumption of, let's look at, say, embedded systems. And if you have something like a wireless sensor network, you want to communicate securely between a server and one of the devices. There are ways of doing this. Either you could have pre-distributed symmetric keys, or you could have a public key approach where you would take whatever the session key is, the symmetric key, encrypt it with the device's public key, and then the device could then extract the symmetric key that way. But we wanted to change this assumption a little bit and say, instead of having traditional public keys, what if we made the device itself the key? So really what we're talking about is we want to dynamically generate the symmetric keys based on the properties of the device rather than a traditional public key system. So we have a general access control model, which is fairly typical. We have subjects, objects, and then we have rights, and then permissions would be a subset of the cross products of those sets. And then we have this additional constraint that we only want to grant access to known trusted devices. So even if you had access to this system, if you're not using a trusted device, you're not going to be granted access. So we've just incorporated this additional constraint. And how we enforce this is that we authenticate the device using its PUF, and then we also generate a dynamic key that's based on the PUF. And that ensures that only that device can decrypt the data that's requested. So we have 3 protocols. In the paper, we have these more formally defined, but this version shows a little bit more of the detail of how it works, and I think it's a little bit more interesting. There's not much going on in the first protocol. Really all that's happening is that you have an administrator who's requesting a set of challenges from the server. And the server is a central server that stores some sort of sensitive data that you're trying to protect. So the server will authenticate the administrator and then respond with the set of challenges, which are the C1 through CM, and then this capital N, which is, it's called a Bloom integer. If you're not familiar with that, it just means that it's a product of 2 primes. And it's also a very large number. So factoring it is not feasible. Once the administrator has this information, then he can access the device that he wants to register with the system, and he enters his username, password, and other things like that, and also these parameters that he received from the server. He inputs this into the client device, which will then send some information to the server. So first, we're going to generate a one-time key, a one-time symmetric key that's based on the user's password, a nonce, and then the set of challenges. And really all we do is we just concatenate all of this and hash it using SHA-256 and use that as an AES key. And then because the server also has the hash of every user's password, the server can also recreate the key as needed. But now if we look at the message that's inside here, we have the challenge response pairs, but we're not sending the responses themselves. We're sending the response squared mod that capital N that we had. And this is all based on the assumption that computing modular square roots is an intractable problem. So once the server gets this information, the server now has a commitment of the PUF behavior, of the challenge response pairs, but it doesn't have the challenge response pairs directly. In order to get the information to model the PUF, the server would somehow have to be able to compute this intractable problem. It would have to be able to compute modular square roots. So at this point, the client has now issued a commitment of the PUF behavior. And then if we look at the authentication and access request protocol, in the formal version, really what we specify is that the client just has to do a zero-knowledge proof of knowledge of the PUF. But in practice, what we've done is we've implemented the FIGA Fiat Shamir scheme, which is a zero-knowledge proof of knowledge, so it fits the formal criteria that we've been aiming at. And what's different about our scheme versus the traditional FIGA Fiat Shamir scheme is that in the traditional version, the prover, or in our case the client, just has a set of secret values. And then they have a set of public values, which are the squares of the secrets. But here, the client doesn't have a static set of secret values. Rather, the client has a set of secret pairs. So the difference is that in our version, what happens is the server will request a random set of challenges, and then the client will then have to compute the PUF based on those challenges, and then generate the proof and go from there. But everything else is identical to FIGA Fiat Shamir, as it's already been evaluated, so it's known to be zero knowledge. So when the client sends this value y to the server, it doesn't leak any information about the PUF. But then we run it one step further, which is that once the server has verified that the proof was correct, and it wants to send the file, send the data to the client, it's going to use the same random value that was initially sent in step 1 of the protocol, but now it's going to request a new set of challenges. So this proof that has to be done is going to be a different proof than the previous time. And that proof will then be used to generate the key that's used to encrypt the file. So because the client, C here, is the only one that can compute this proof, then that client is the only one that can generate this key and decrypt the file. But notice that the proof is never actually sent from either party here in the last step. And so that means we're not actually repeating the proof with the same random value, which means we're not leaking any additional information. Okay, so if we look at the performance of this, because we've actually implemented this, and if we look at just the client side, because again, this is our main focus because we were looking at sort of low power embedded systems. What we found is that the amount of time to compute the initial authentication proof and then also to generate the key, which are these blue and green portions here, it's basically constant regardless of what the size of the file is. And they're essentially equal to doing symmetric key encryption on a small amount of data. So this here is 10 kilobytes of data. And I've plotted this both linearly and logarithmically because that's the only way you can really get the true picture here. That what happens is the amount of time to decrypt the file, to do the symmetric key encryption, grows linearly with the size of the file. But the amount of time to do the proof and key generation is constant. So this means that we're not really imposing much of an overhead on the client itself. We're essentially imposing twice what the symmetric key encryption already imposes, which is not very much. What's not included in this picture is that the PUF adds about 2 milliseconds, but this is a parameter that we can actually control because we specify how long the PUF will execute. But still, this is a negligible amount of overhead. The symmetric key by far becomes the dominant factor of the performance in this case. On the server side, the picture's even nicer because on the server side, the server only has to do a couple of multiplications. It doesn't have to do any computationally expensive work. So the overhead on the server side is very negligible and it's very scalable. So this isn't going to cause a burden on the server side. So if we take a step back and say, well, what does this really say? What have we really done here? Well, what we've done is we've generated a way of doing a lightweight key exchange. Basically, we've taken the public key type of approach, but by incorporating PUFs to generate the keys dynamically, rather than using RSA and modular exponentiation, we've cut the performance time drastically. Basically, doing one of the PUF key generations takes about a fourth of the time of the corresponding RSA evaluation. So if you have a system where you're going to be using a lot of keys in your symmetric key system, you're going to be generating a lot of keys that are unique for every session, where in that case you would have a lot of RSA overhead, a lot of public key overhead, because each one of those keys you would have to do a separate modular exponentiation. If you have that type of setting, then our approach will actually reduce the overhead on the client side. And it makes the lifetime of the power supply and the batteries and other things like that a lot longer, because it reduces the work that has to be done. So it has this nice feature that it has properties similar to public key cryptography, but without some of the overhead. If we look at some of the details of the security analysis here, the first thing that comes into play is that the key size, or the size of the PUF, is vital. Because one of the things I didn't really say, one of the details I didn't leak earlier, is that the intractability assumption regarding modular square roots is that the size of the modulus is approximately the same as the size of the modulus for RSA. So if we really want to compare our scheme with RSA, then we have to have 1024-bit PUF outputs to be equivalent to 1024-bit RSA. This becomes prohibitive on the geometry of the chip itself. You don't necessarily have that much space to have a PUF that's that large. Instead, what you can do is you could have a 128-bit PUF, which would be a fairly reasonable size, and execute it 8 times, buffer the responses, and concatenate them. And that would give you a 1024-bit response. So there are different games that you would have to play here to really balance the trade-offs between having a good size of key, but also having it fit on the device that you want. Our trust assumption, we're assuming that the server is trusted. The reason this is acceptable is because if the server is not trusted, then that means the sensitive data on there, if the server is compromised, then the attacker already has access to the data. They don't have to break our system. So it's a reasonable assumption. And the last one here also is that even if you do get access to the challenge response commitments that we have, that doesn't help a probabilistic polynomial time adversary to impersonate one of the devices. You really have to have the raw responses. Okay, so that was the first work that is really sort of the most mature of everything that we've done, because we've done a lot of formal analysis and protocol analysis and implementation work. So I want to shift gears a little bit and talk about these two newer works. The first one is called PAIR, which is Physically Enhanced Authentication Ring. So PAIR is really just in a lot of ways, it's an adaptation of the work we were just talking about, but we're adapting it to web-based authentication. Specifically, we want to have privacy-preserving authentication. So PAIR has a couple of nice features to it. It allows for unlinkable logins. So one user could have multiple login usernames for the same website, and the website would not be able to link those. They would have no way of knowing it's the same user. There are some very nice reasons to have that. It can also be adaptable for organization-wide credentials. So if you have a small business that has access to an online banking site, and you want all of the managers there to be able to use the banking application, they could use PAIR as a single unified login without having to share passwords and other things like that. Pair is also a portable device, and one of the nice features of it is that because it's a dynamic challenge response authentication, you can use this on untrusted public terminals, because unlike a traditional password response, you don't have to worry about keyloggers because of the dynamic nature of the challenge response. And then also it simplifies maintenance of passwords, that instead of having to remember a large number of passwords for every website, you just have a single password, a single PIN for your pair device, and it will automatically generate passwords for all of the websites that you need. So I said this is really similar to the work that we've already done, that we were describing before. So I won't go into the details quite as much. But we start off again with an enrollment request, and then the user gets this website ID and user label from the service provider. So here you're going to have the ID of the website, and then you have your username. And you take that information and also your PIN for the pair device, and that becomes this H result. So it's a hash. And that becomes your input to, we call it PGV, which is Password Generator and Verifier. But really what this is it's a PUF. And you wouldn't actually just have a single one of these. You would actually generate a large number of these hashes. So you would use a nonce for each one. But it's the same principle, that you just use this hash input into your PUF and get the response, and then you send a commitment to the service provider. And then later when you're trying to access that service, especially when you're trying to do some sort of sensitive transaction, again, you would initiate your authentication request, and then you would use your pair device, which has the PUF in it, to generate the proof that will be used to authenticate you. What's nice about this is because of the fact that it's dynamic, you have to have the pair device. So you can't have any sort of replay attack here, because you wouldn't be able to forge another proof. So it's a dynamic challenge response protocol. But again, it's very similar to the work that we've done. As I said before, this is a privacy-preserving authentication scheme. Users can have multiple labels for the website, and the service provider doesn't necessarily know. So there's unlinkability between the logins. There's also the portability aspect, that because of the dynamic nature, you can use it with untrusted terminals. And then you can also have the organizational anonymity. Okay. So both of those were using PUFs for authentication. This third work that I'm going to present is a very different work. So we call these PUF rocks. And a rock is a read-once key. So the idea from a formal perspective is that if you talk about an obfuscator O, so the obfuscator is a special program. What it does is it takes a program as an input, and it returns another program that's functionally identical but indecipherable. So you can't tell that the output of this obfuscator is the same as the original input. So it's just talking about program obfuscation. Well, a read-once key really is just sort of a special type of obfuscator, but instead of obfuscating the entire program, it's just going to obfuscate the key. And the idea here is that once you use this key, it's no longer valid. So you would have your original key, you obfuscate it, and once that version of the obfuscated key is used, it's no longer valid. If you had a different obfuscated version of the same key, you could use that, but no longer that original version. So the idea here is that you have cryptographic keys that you can only use once. Once you use it to decrypt a message, it's destroyed. And there's been a lot of interest in these in the cryptographic community. And it's also been shown that you can't actually create them from algorithmic processes alone. That you have to have a sort of trusted hardware that will forget the key after it's used. The type of memory that's been proposed for this is called oblivious RAM, which is, it basically says that once you store a key in memory and you use it to decrypt a message, then that memory forgets that key somehow. This is the abstract version. So the question is, how? Is that what you were going to ask her?
No, core memory. Core memory. I'm dating myself. Reading it destroys the value.
That's basically the idea. We've been looking at how to do that with PUFs. But the idea is that you do have to have some sort of physical layer of trust. So some of the applications that you can use here, well, you could do delegated signatures. So if I wanted to let one of you sign a document on my behalf, I could take my private key, encrypt it with a read once key, and then when you would go to sign a document, you would use your read once key to decrypt that, get my public key, sign it, and then that version would be completely destroyed. So you could delegate signatures in that way. Self-destructing messages. If anyone remembers Mission Impossible, this message will self-destruct in 10 seconds. You could do things like that. Usage control, one-time programs. You have a lot of these applications, but as I've thought about this, one of the neatest applications, one of the coolest things, is it also creates a very strong defense against some very powerful hardware attacks. So fault injection, differential power analysis, these are attacks that rely on repeatedly executing a cryptographic algorithm with the same key, and in the case of fault injection, you just insert a power surge at key points, and then after enough iterations, you leak enough information to determine what the key is.
So in this application, what you said is you use the key to decrypt once, and then the key is forgotten. But what prevents the plain text message from being?
In the case of delegated signatures, yes, that was the case. That once the decrypted message, in that case, was the public or my private key, which then, yes, that would also have to be destroyed. So you do have that issue as well.
So how is that addressed? So is that solved or?
So we've actually got a system-on-chip type of design here that everything is done as a single process. That you would issue the request to sign this message, and you would have a core that will generate that will decrypt the private key and then do the signature and then return the response. But all of that is done internally without actually storing the private key. But for some of the other applications where you just have a symmetric key that's used once and then destroyed, you don't have that issue. So, to sort of formalize this, we sort of have it as kind of an extended Turing machine. It's also, I guess you could also say it's a finite state machine. Basically, we've just extended these traditional notions of a machine to separate between symbols being instructions and input being the messages that are being encrypted or decrypted. Typically, you wouldn't have that distinction, but it makes it nice for our formalism. And we have these two primitives. We have the encrypt primitive, which once you've reached a certain instruction and a certain state of your machine, when you encrypt that message, the first time you'll transition to one particular state because it would generate one key to encrypt it. The second time you would go to a different state. So there's this non-determinism within this machine. And the decrypt primitive, similarly, the first time that you would call this from a given instruction and a given state on a given encrypted message, the first time it will decrypt it successfully and transition to one state. Any additional times, it would transition to a different state because the decryption would fail. We do have this parameter epsilon down here, which is that there is a probability of bypassing the system, because if you can guess a certain value, then you could break the system. But this is equivalent to being able to guess a 256-bit key. So it's unlikely to be, it's infeasible, but we have that there as a parameter. So the high-level view of the system is this, that we have everything is on a single processor. We have a core that's sort of the main processing core, and then we have a cryptographic core of some sort. Really what you could have is instead of having the processor core on the chip, within the system on chip, this communication from the processor core to the crypto core could be across the bus. The main thing that we need is we just need this bottom portion all on a single chip. When the cryptographic core needs to get a key, first it initializes a register with a certain value, and then that value becomes the input to the PUF, and the output of the PUF becomes both the key and also it overwrites the register value. So every time you pull the PUF, you'll get a new value, and the value that's stored in this register will be overwritten. So it's inherently destroying the previous value that was stored. So this feedback loop is really sort of the key. And when I'm talking about a cryptographic core here, this could be something that you could incorporate PUFROCks into a traditional cryptographic processor, something like a TPM. So we're just assuming this is a core that's like a TPM designed to do special cryptographic operations. But you don't have to necessarily have that particular chip. So the idea here is that it's really similar to hash chaining. So if you're familiar with hash chaining, you start with a key, and then you take the hash of it, and that becomes your next key, and then you keep going, and this becomes a way of generating a sequence of keys. But the difference is that with PUFROCks, they're based on the hardware, not on algorithms. So you don't have the same type of algorithmic process involved. So especially with the ideal PUF assumption that we talked about earlier, you have less determinism. So if two devices started with the same initialization, you would get different sequences of keys as a result. But one of the other features is that the keys are never externally stored. They only exist within the processor themselves. So that means you can't eavesdrop on the bus and determine what the key is, because the key is never sent across the bus. It's never communicated with any external peripheral. It never exists in memory, so cold boot attacks won't work. And like I said before, you could incorporate this into a traditional cryptographic processor. But there are some problems in the design as we have currently proposed it, this initial basic version, which is that it really requires you to encrypt a message and then decrypt it, and then encrypt a new message and then decrypt it. And you have to do everything in this exact order, which is not good. And you have to reinitialize everything in between. So we have to look at some optimizations to make this actually practical. So the first thing is, instead of having one register, we have three registers. We have a sort of seed register, and then we have separate registers for the encryption and decryption. And so the first time you encrypt a message, the seed register will be used as input to the PUF, and then the response will become the key, and that then goes into the encryption register here. So that way, the second time you encrypt something, the encryption register value will be used as the input. And so you have a feedback loop there. And then later you could, once you wanted to decrypt a message, then the first time you would copy the seed register into the decryption register. You may have to pull the PUF a few times to sort of fast forward. So if you wanted to decrypt the third message, you would have to execute it a few times to get things synchronized. But again, then that would let you generate that key, and you couldn't go backwards. We also have this cache of the error correcting codes. So that way, you could have up to a certain number of keys that are valid at any point. And then once that key is used to decrypt a message, then you just mark that bit in the error correcting cache as invalid. So that way that key is no longer able to be used. You could also adapt this so that you don't have keys that are only good once. You could have them used n times where you have some finite number of times. But this allows you to have an expiration to your cryptographic keys. Here's a sample workflow. The idea here, again, is that you start with an initialization value that goes into your seed register. Then you would generate 3 keys to encrypt messages. And then you would specify that you want to decrypt the second message. So you have to move the seed register value into the decryption register and advance it twice by pulling the PUF, and then invalidate the value in the error correcting cache. And then you would generate a new key the next time you called encrypt. And then later on, I didn't really get into the details here, but after a while, you need to use the fact that some of those invalidated error correcting codes need to be overwritten because you want to generate new keys. And we have this sync operation. Again, I won't go into the details of that right now, but the idea is that once you have a certain number of spots that are available within your cache, then you can clear that out and you would update the seed register. And what this does is it prevents you from having to go back to the initial X value that you used. Because once you've generated 50 keys, you don't want to have to go back to this initial seed value of X and advance the PUF 50 times to get things synchronized. Instead, you would advance the seed register at certain key points. Again, we don't have enough time for going into the details there. So, our prototype implementation. We have this nice device that has both an ARM processor and an FPGA on it. And on the ARM processor, we were using a cryptographic library there. And then we implemented the PUF and the register within the FPGA. Because we didn't really need to do anything specific with the cryptographic operations, that's why we just implemented it here. But there's a very big vulnerability here. Does anyone have any idea what it is in this current design? It breaks one of the design principles that I had originally talked about, which was that everything had to be on the same chip. Because once you have something like an interconnect or a bus, you can eavesdrop on that. So our current prototype has this big vulnerability that the key would be transmitted in plain text across this interconnect, and you could potentially eavesdrop on it. But that's why this is just a prototype. It's just a proof of concept. In a real implementation, you would have everything on a single chip, and so you wouldn't have that vulnerability. Okay, so conclusions from all of this. PUFs are, I think, very interesting. They're unpredictable functions that the behavior is tied inherently to a physical instance of a piece of hardware. And the traditional uses of PUFs that have been proposed have typically been for things like secure key storage. But I think we can actually do a lot more with that. And if we integrate PUFs into cryptographic protocols and key exchange and other things like that, then we can get some very interesting results out of it. And with the last project, PUFs can be used as a means of trusted hardware to implement that oblivious RAM that cryptographers like to assume exists. So, any questions?
How are PUFs different from just a key hash function?
So it goes to the fact that the behavior of the PUF, the mapping from a challenge input to the response, there's no algorithmic process behind it. It's entirely determined by the variations within a piece of hardware itself. So in one respect, it's very similar to a hash. The difference being that if you use that same hash algorithm and you use that same key on multiple devices, you'll always get the same response. You'll always get the same behavior. But PUFs are inherently unique to each physical hardware device.
Right, but I thought you said earlier in the beginning of your talk that given the same input, it was shown that they output the same.
Within the same device.
Right, but you could change the key for the hash, and then it would be equivalent. Right?
But then that gets into assumptions of trust regarding the key storage and other things like that. PUFs reduce the level of trust assumptions. Basically, it makes it so that it is physically impossible to transfer the key like you would have in a keyed hash. It reduces the trusted computing base in some ways. Okay.